Hi, my name is Savin, and I work on the machine learning infrastructure team at Netflix. So my team is tasked with providing support for all of data science activities that Netflix is involved in. And over the last few years, my team has been working diligently on this new machine learning infrastructure that we recently open sourced. And over the next 30 minutes, I'm going to talk about the philosophy behind it, and as well as give a brief introduction to that. So let's get started. Since we are at a conference with scale in its name, it makes sense to start with that. So Michael Stonebreaker, who is a Turing Award winner, did an amazing work in database systems. He had a very handy categorization of data systems around these three dimensions: volume, velocity, and variety. And modern machine learning systems are very much akin to data systems of yore. So by volume, what we mean is machine learning systems which process a huge amount of data, a huge volume of data. By velocity, machine learning systems that might need to sort of like train on a fire hose of data, or need to rely on very low latency predictions. And then the third one, which not a lot of people essentially talk about and have had a tendency to gloss over, is all the big, wide variety of machine learning systems which don't really fall into each of these buckets. Now, when it comes to Netflix, I'm sure that most of you here would have at some point subscribed to our service, and this is the first thing that you see when you log into Netflix on either your TV or your computer. This is the Netflix homepage. Every single aspect that you see here is driven by an algorithm. The shows that we recommend you, the album art that you see over here, the rows, the ordering of the rows, every single thing. And to assemble this page, we definitely rely on a huge volume of data. We need to serve these recommendations to more than 170 million members all around the globe at a very small latency. So the volume and the velocity buckets, these kind of systems satisfy. But behind the scenes, Netflix uses machine learning in a lot many more use cases, right? So we are one of the world's biggest studio. We spend more than $16 billion every single year deciding what content to buy. And somebody needs to make a decision. What is the value of any given piece of IP that comes our way? When we are producing a show, before we greenlight it, while it's being produced, we need to estimate how many people are going to watch it, how many net new subscribers are we going to gain? Is this actually an efficient use of money that our subscribers are giving us to us? We happen to be one of the world's biggest content distribution networks. So every single time you hit play, that content is being streamed from a physical hardware device that is kept at your ISP. So every few hours, we need to make a decision what content is going to be popular in your neighborhood, so that we can seed that box with that particular piece of content, so that you don't run into rebuffers. As one of the biggest subscription service, we also need to be sort of like in the forefront. How do we fight financial fraud? How do we make sure that the way we process payments is as efficient as possible? So as you can see, like our data scientists are kept busy with all of these variety of different problems which need a variety of different skill sets. And as it happens, there's no one single piece of machine learning infrastructure that can necessarily solve that. And that was the problem that my team ran into as well. And that's when we started to think like, okay, what is it that we can build that can help all of these data scientists, all of these people who are tasked with solving these problems day in and day out, be more successful at their job? So to begin with, let's talk about how data scientists functions. What does their day-to-day look like? And for the data scientists in the room, I'm pretty sure you'll identify yourself with the story. So as a data scientist, you are tasked with figuring out a solution to a business problem. Ultimately, at the end of the day, you need to drive value by optimizing certain metric. And what do? You spin up a notebook, maybe Colab on GCP, maybe a Jupyter notebook, maybe Polynode, and you get cracking. There are a whole bunch of machine learning libraries out there. Megan in the morning spoke about TensorFlow. We're going to have folks from Facebook who will talk about PyTorch later today. So there are a whole bunch of tools, a whole bunch of algorithms that you can just like pick off the shelf and get started. But machine learning without data doesn't really mean anything, right? So you need to have a way to access your data. And this is all good and fine as long as you are iterating on your laptop. But then this data needs to come from somewhere, right? You need to figure out how to write these ETLs, which arrange your data in a format that you can consume in sort of like a meaningful manner. So you need to figure out how to actually write that ETL, schedule that ETL, and so on and so forth. then there will be a point in time when your resources on your laptop are just not good enough. So you'll be like, hey, can I now move to a bigger laptop? Can I move to the cloud? How do you actually do that, right? Like these days, people rely on Docker. So then you start thinking about, okay, how do I containerize this? How do I write this Docker file? Writing Docker files. For most engineers, it's super difficult, expecting somebody who doesn't really have a formal background in software engineering most times, highly non-trivial. Then a model by itself doesn't really mean much, right? Like this model has to be put into production. This model has to be used in some way or form, which often means more containers. You're either hosting your model as a microservice, or you're just doing some batch compute on your model, scoring some requests, and then storing it somewhere. All of this will ultimately, at the end of the day, power some sort of UI, some sort of business decisioning, and your stakeholders will then take a look at these results, and they will be like, okay, like either a thumbs up, good work, need to do more, need to iterate yet again, or they would be like thumbs down, and then you would be like, hey, why did I go through all of this? Can there be something that can just like make my life easy, and so that I don't have to spend like months and months just like getting to this very last state? So as you can see, like here's an individual who has training and deep expertise in data science. But if you actually look at the actual amount of data science work that they are doing, that's very minimal. Most of their time is consumed by engineering work, which ultimately, at the end of the day, seems like a productivity hog. Data scientists, it's true at Netflix, and I'm pretty sure in a lot of other organizations as well, are often the most expensive resources. Like machine time is super cheap. The amount of money that you pay to like any of these vendors, that's also like is dwarfed by the salaries and the other resources that these data scientists are afforded. So then the necessary question is, what can we do to make sure that like this iteration cycle, this cycle from prototyping to production, back to prototyping, iteration is made as quick as possible, as efficient as possible, in a manner that doesn't really enforce a good amount of tax on data scientists, and they can focus just on data science and less on engineering. Now, one other way of looking at the same problem is looking at it from the lens of what is the data science stack? Like the story that I told you about, it's a story in abstract, right? But let's get into the specifics. Let's get into the weeds of it. Now, when you start with any machine learning problem, the very first thing that comes in is, okay, where is my data? Where is my data lying around? As a data scientist, you often don't really care too much if your data is stored in S3 or HDFS, or is that some CSV file stored in like somebody's cabinet, so on and so forth, right? The next thing that comes in are compute resources. You would need access to GPUs. You would need access to boxes with like a lot of RAM. You need easy access to compute resources. You don't want to like go through 5 or 6 different UIs and like figure out like special fancy ways of just scheduling your compute on some compute cluster. And these days, Kubernetes is tout de jour. People use some sort of like container orchestration system. So internally at Netflix, we use something called Titus, which predates Kubernetes, but the concepts are pretty much the same. On top of this, you need some sort of orchestration layer, because you need to make sure that when you move to production, there is some scheduler, some orchestrator that is orchestrating your compute on top of this container orchestration system. And all of these container orchestration systems, they have containers in their words, so you need to make sure that you have some way of generating these Docker images, playing around with these Docker files, some CI/CD infrastructure to just package your code and be able to deliver and deploy it. Now, machine learning happens to be an iterative task, right? So, which means that experimentation needs to be a first-class citizen. But then how many data scientists actually treat it that way, right? Like versioning and metadata management, it's kind of like flossing. People agree that it's nice, but nobody actually really does it. And then when you run into problems, when you're like, hey, just maybe if I had kept track of these metadata, this exact version of code that ran, life would happen much more simpler. But then you can't really go back and fix things in the past. The thing that comes on top of that is your actual development environment, right? Like, are you using a Jupyter Notebook? Are you using RStudio? Are you using PyCharm? Are you a Vim person or an Emacs person? And you want to make sure that, like all of the stack below you kind of like supports access, like good access to all of that. At the very top are the machine learning libraries, right? Like as a data scientist, you want to exercise your full freedom that, hey, do I want to use TensorFlow or do I want to use PyTorch? Does scikit-learn help me or do I actually want to just go ahead and write my own implementation? Now, as a data scientist, you care about the top of the stack, right? You really care about whether you're using TensorFlow or PyTorch, but you don't really care if your data is coming from S3 or is it coming from HDFS, right? Now, but as infrastructure engineers, for us, we deeply care about how the data is laid out. Are you making efficient use of resources? How is your container orchestration system set up? How is packaging being done? How are these versions managed? What is the experimentation management system and all? And it's all very, very hard, deep work that needs to be done. But then at the same time, a data scientist would very much prefer if, as systems engineers, we took opinions on that and just kept their life easy by making sure that they have the absolute amount of freedom at the higher levels of the stack. So to solve this, we built Metaflow. So Metaflow is the machine learning framework that has been used at Netflix for the last 2 years. And Metaflow is essentially an opinionated wrapper around this deep stack of machine learning tooling, where we didn't really try to reinvent the world, as I said before, right? All the problems, all these productivity hogs that the machine learning practitioners are running into, there are solutions for that, but there is no one coherent story around it. So instead of reinventing the world, we just try to make sure that, hey, can we just collect all of this knowledge, all of this tooling that has been built already, and present it in a way such that the data scientists can just focus on data science, and they don't really have to worry about, like, hey, is my code getting versioned right now? Am I making the best use of resources right now or not? So Metaflow, at the end of the day, it's supporting 2 major machine learning activities. One is building your machine learning models, training your machine learning models, and the other is deploying them in real-world scenarios. And both of these involve humans at the end of the day, right? Like, we are not at a stage where somehow the problem can figure itself, like how to solve it best, and then there's an ETL, voila, and things get deployed automatically. So any tooling that we build has to keep humans in perspective, has to keep in mind who the users are, what are their skill sets, what is it that they really want to do, and how best can we design something that sort of like helps them rather than create a steeper learning curve. So let's get into the weeds of it. Let me give you a very brief introduction of what Metaflow looks like. What is it like to play with Metaflow? So this is inherently what any piece of machine learning code looks like from a 30,000 point of view, right? So you have like some function that you write, some imperative code, getting some data, training a model, storing it somewhere, 500 lines of code, 1,000 lines of code, and to execute it, you just like type Python, you have script.py, and you get done, right? Now, how do we make improvements to that, right? So one way you can do that is, what if we allow our users to sort of like declare their computation in terms of a graph, right? So in this scenario, you can think about these 5 steps. In the start step, you are sort of like getting data from some data store. Maybe you are training 2 different versions of model A and B. And then in the join step, you are figuring out which model performs better. And then in the end step, you might be deploying your model somewhere, right? Now, this notion of arranging your compute in a graph, it's not new, right? Like, there have been workflow schedulers, Luigi, Airflow. All of them have some notion of this DAG. So there's literally nothing new out here. But one thing that most of these schedulers miss out on is every single node of the graph is kind of like assumed to be an idempotent unit of execution, and state passing is kind of like left as an exercise to the reader, which Metaflow provides first-class support for. So for example, in this case, let's say you have any instance variable, say x, and you assign a value to that, then the values are available to every single subsequent step of the graph, and Metaflow will, in the background, actually snapshot the entire state and store it in the data store, which happens to be S3 for us. Now, this yields a lot of different benefits for us. So for example, you decide that, hey, maybe the code that I wrote in step B doesn't really work well, there's an error, there's a bug, then you can just fix that particular step and you can just resume your computation right from step B. It could be a scenario where in your step start, you're loading a huge data frame which took let's say 20 minutes of time on your query engine. Now you don't really have to pay that tax anymore because that data is already snapshotted for you, and then we bring that data back for you every single time you're resuming any step. The other problem that people run into is that, hey, okay, this works fine on my laptop, but now I need to get access to much bigger resources. Right now I need to have this thing run on, let's say, 500 gigs of RAM, right? How do I actually go ahead and do that, right? And at that point in time, there's a huge gap that the data scientists need to cross, and oftentimes they need to lean on software engineers to figure out how to schedule any sort of remote compute. And Metaflow lowers that bound significantly for people. So with this decorator annotation at resources, they can very easily just specify that, hey, for training this TensorFlow model that I have, I need 16 CPU cores and I need access to a GPU. I need to perform this massive data frame operation and I need 200 gigs of RAM. And what we are going to do is we are going to take this compute and transparently we are going to actually schedule it on the cloud. So in our case, inside of Netflix, that happens to be Titus, which is our container orchestration system. In the open source version that we have, we rely on AWS Batch, and then we have a Kubernetes integration coming up. So that's really helpful for people, right? Because now all of a sudden, if they run into any issues, any sort of resource constraints, they can easily just use the cloud and get their work done. The other important construct that Metaflow introduces here is this notion of for each. One of the things that machine learning practitioners like to do is, here's my model, here are a bunch of hyperparameters, and I just want to train all possible combinations of my model and then figure out what's best, right? And that means that that requires a significant amount of resource consumption, and how do I do that very easily? So in Metaflow, you can have steps which can just depend on an iterator. So in this case, the self.cred is a list, and you can very easily just have the step A iterate on the elements of that list. And for every single step, in case if you define a specific resource, we would actually launch an individual container on the cloud. So for example, in this case, let's say you are training your TensorFlow model with some arbitrary parameters. Let's say the number of parameters you have are 3, then you can very easily just request 3 different instances with 8 GPUs and 200 GB of RAM. And we have internal use cases where people request 10,000 containers in parallel for training some of the models, right? So we have use cases where people want to train country and language and title-specific models, and if you just blow out the cardinality, that's too huge. So just another point that I want to mention here is, a lot of people might be wondering when I said that, 10,000 containers and so on and so forth, that's a huge amount of compute, and that costs a lot of money as well, right? But then at the same time, we live in a world where spot instances are really, really cheap, and the fact that Metaflow is already snapshotting your stage, and you can add automatic retries and everything, it just makes your compute a lot more efficient than it used to be before. And you can very easily just carve out specific pieces of your workflow which need specific dedicated instances. So compared to, let's say, previously you might be needing an instance with a GPU for the entire length of your workflow. Now you can just isolate it for the actual workflow step that needs GPU resources. Now, one big problem that we observed our users face was around data access, right? It's all good and fine that I can do a hyperparameter search and I can have a very wide for each, but then each of those nodes are also actually, they need some data, right? And usually people have been trained that, oh, data means that you need to go against a query engine, and most organizations have a fixed size Spark cluster, for example, and then let's say if I'm running a very wide for each, suddenly I'm inundating that Spark cluster with a whole bunch of queries, and each of them will slow everybody else down in the organization. And more often than not, what people are doing at the end of the day are, here's my data partition, and I want all of that data as quickly as possible. So Metaflow ships with its own S3 client, so we actually saturate the entire network bandwidth available on the instance, so that we can get the Parquet files and we can load them and store them as in-memory arrow representation. So you heard Wes talk about some of the good work that he has been doing. And we make that available to our users so that they don't have to pay the tax of like going against a query engine over and over again. And that has been really, really powerful for our users internally, and we have been seeing massive adoption for this feature externally as well. The other big issue that people run into is around third-party dependencies, right? Machine learning is a very, very fast-moving field. Every single day, every single week, there are new advances that are being made, new versions that are coming out. And the entire if you look at the dependency tree of any of these machine learning libraries, it's really huge. And more often than not, they don't even pin the specific versions of dependencies. So even if you're installing TensorFlow today, and if you install the same version of TensorFlow tomorrow, you might just end up picking up different versions of downstream dependencies. So even though from your side you didn't actually change anything, the results that you might get might be entirely different. Things might not fail. Things will be just different. And with the state of tooling available right now, it becomes really hard to capture what those differences are. As well as at the same time, in many organizations, people are like, hey, we'll perhaps settle on a specific version of TensorFlow or a specific version of PyTorch, and we'll make available a Docker image with all of these blessed versions, and people are supposed to only use that. Now, what happens when you actually have to move to a newer version? What happens to the workflows that you have already deployed on your previous versions? What happens if you have to be on the bleeding edge and try out a new feature that just recently launched? It becomes super, super complicated at that point in time. And also deploying or installing many of these packages is not really trivial, right? Like if you have ever tried to install TensorFlow GPU on your own, it's not as straightforward as just doing a pip install, right? So we rely on this amazing package manager called Conda, which has most of the data science packages available in its repository and makes installation super simple. And behind the scenes, what we do with Metaflow is we actually snapshot the entire transitive dependency graph for you, and we store that in the data store. So now every single step that you see is inherently a closure for us, where you have defined your dependencies. We have actually captured at that specific moment what that dependency tree looked like, so that we have complete confidence that at any point in the future, we can regenerate, rehydrate that environment for you. We know what sort of resource requirements you need, and coupled with both of these and the user code that we version and snapshot every single time for the user, we can take this unit of compute and we can orchestrate and schedule it anywhere, be it your laptop, be it the cloud, anywhere else. And that helps a lot in reproducibility. So, okay. So the next thing is around versioning, and the thing that I spoke about, flossing. So what Metaflow does behind the scenes every single time you execute your workflow is that it assigns it a unique identifier, which just increments by 1 every single time you execute. And then you can go back in time and you can access the state of your workflow, because we have been snapshotting every single instance variable of all the steps of your workflow, as well as we can recreate the environment that you specified. So now you can go back, you can look at, hey, this model that I executed or this workflow that I executed a month ago, what is the state of that workflow? What were some of the attributes of that model? How does that compare with the model that I just trained with this new workflow? Or, my coworker was actually doing some experiments more than a year ago, and I want to see, how my new line of research pairs up with that. So that's really powerful, and that really helps our users when they don't really have to actively think about versioning their workflows or versioning their code. All of that is just handled seamlessly by Metaflow behind the scenes. Now the other component, after you've kind of like built your machine learning workflow and you're happy with the model that you've trained, is what do you do with it, right? Like a model by itself is worthless unless it's actually used by somebody. So Metaflow allows people to deploy their workflow in production very seamlessly. So up until now, the situation in organizations before Metaflow, or at Netflix before Metaflow, was the data scientists will work on some prototype workflow, and then it would be the responsibility of a data engineer or a software engineer to take that workflow, translate it into some production quality code, and deploy it on top of some scheduler. with Metaflow, we just take the user code and we translate that into a language that the DAG schedulers can understand. So internally, we use a scheduler called Meson, and the open source version has integrations with AWS step functions, and it can very easily also pair well with Airflow, for example. So now once you have deployed your model into production, right, like anything that goes into production, it's bound to fail at some point in time, right? Like you can never guarantee that things in production, once they work, are always going to work seamlessly. And at that point in time, again, given the fact that we are snapshotting the entire state of the workflow at every single time, our users can very easily verify what is the state of their workflow, what's happening where. A lot of times people have tried to build kind of like a universal UI for machine learning use cases. And in practice, we've seen that all of these machine learning workflows are very different from each other, and every data scientist has a very different notion of what is it that they actually want to monitor. So instead of building one UI that rules them all, we inherently just gave them the tools where they can just use a notebook, and with small little steps, they can just like figure out, hey, what is the stage where my workflow is at? What is the state of my workflow? What are like some of the parameters, some of the values? And the fact that we are snapshotting every single aspect, they don't have to go back and be like, hey, now I need to log this parameter as well, or that parameter as well. All of that is kind of like taken care of behind the scenes. The other aspect is, so we've spoken about like, training workflows, or let's say scoring workflows where you might be doing batch scoring, but a lot of times you just want these models to power some system, right? It could be another service, it could be an internal UI, and we have found in practice that a much better interface between engineering teams and data science teams, instead of being the model, is just a simple API. So Metaflow also has this hosting component where you can just go in as a data scientist, write up your Python function, and then Metaflow will take care of just hosting it as a microservice, and then it will scale it up and down as needed in response to the traffic. So in this particular example, there's this result attribute, where you're referencing this instance variable x, which comes from this workflow. And because we know that the value of x is 3, the return result is 3 over here. So these are some of the features of Metaflow. So we released Metaflow at AWS reInvent in December, but Metaflow has been in production inside of Netflix for close to 2.5 years. Most of machine learning, except for the recommendations use cases, use Metaflow internally. And we have seen a good amount of adoption over the last 2.5 years. There are like a whole bunch of big and small enterprises that are using Metaflow. So if you guys want to give Metaflow a try, I would highly recommend going on to our website. We also have a hosted version of Metaflow, so in case you don't have access to cloud resources, you can go to metaflow.org/sandbox, and we'll provision a cloud instance for you, and we'll cover the bill while you play around with it. So in summary, as we saw before, models are a very tiny part of an end-to-end ML system, and it's really important that the data scientists are allowed to focus on data science and less on engineering. And with proper tooling, which focuses on the actual human aspects of data science, it's actually possible to do that. So, thank you.
Question here?
Yes.
What is the main thing that Metaflow can do that Airbnb's Airflow cannot do?
So Airflow and Metaflow are kind of complementary, in the sense that Airflow is a scheduler. You can think of it as a production scheduler, while Metaflow is a machine learning framework, right? So with Airflow, for example, I don't think you can get experimentation management, or if you have to pass state around, I think they have some projects coming in place, like, don't even remember the name, but another way of thinking of interaction between Metaflow and Airflow would be that once you're ready to go into production and your production scheduler is Airflow, at that point in time, you can export the Metaflow DAG on top of Airflow. So we're not a replacement for Airflow. We work with Airflow.
Building on that question, how does it compare with other frameworks like Kubeflow, TensorFlow Extended? Mm-hmm. And corollary to that question, Who's the typical user for this tool? Because those other tools, you don't see like normal users using it. It's mostly like large companies.
Sure. So when it comes to Kubeflow and TensorFlow, I think one thing is that they're very closely tied to the particular ecosystem. So Kubeflow, by its very name, is Kubernetes. TensorFlow Extended, by its very name, is pretty much tied to the TensorFlow ecosystem. And if those are not your choices, then it's not a good fit for you. So when we started building Metaflow at that point in time, we looked at all of these projects, and these projects were at its infancy as well. And we failed to find an end-to-end solution that worked for our use cases. If Kubeflow, TensorFlow Extended work for your use cases, the set of assumptions that they have, they are excellent tools. But for us, it was really important that we don't tie our future with one particular set of technology, and we keep ourselves as agnostic to all the tooling that's coming out. And I think there was one more question on like who are the intended users. So the intended users for us, for at least the open source version, are people who are looking at an end-to-end solution that has been proven out well in production. Those are the kind of users that we are looking at. Also, a lot of companies these days are wondering, what kind of investments they need to make in the machine learning infrastructure ecosystem, given the fact that there are so many competing projects out there. So, yeah, I mean, if you are in that frame of mind, we'd be happy to talk to you. Yes.
So we have been a user of Airflow, and we build a lot of infrastructure around Airflow, which is a little bit like you show. Mm-hmm. And we are moving to Kubeflow right now. So I think I like a lot of things that you show. But for example, in my organization, I will have two problems. So the first one is all our online services are basically in Scala. Scala. All online services. Okay. And even our ETL, I probably start to have 60% of our ETL were in Scala. Mm-hmm. And believe it or not, I have a lot of, for example, in my organization, a lot of statistical learning. So a lot of people who are doing R, mm-hmm. for which, that kind of workflow will not work. So want to hear what you have to say.
Sure. So one of my slides had many more features at metaflow.org. So we have equivalent support in R. So our internal users are split across Python and R users. So everything that you saw, we have functionality for R users too. And then historically, most of the data engineering work at Netflix was also done in Scala. And some of the low latency online serving systems that we have were also written in JVM for the recommendation use cases. Now, Metaflow is not really an all or nothing ecosystem, so you can very easily just pick the pieces that you really like. So for example, you can just take the authoring part of Metaflow, which provides you a way to train your models as well as dump your models in your data store and be able to reference those. And then you can have your online scoring systems written in any other language. As long as you can serialize those models and make use of them, you should be good to go.
All right, let's thank Savin one more time.